Hi. So we've spoken about why the transformers, issues with original sequence models, that one thought vector, the gradient flow, the things in sequence and not in parallel. And then we spoke about the different building blocks of the transformer block, starting from the self-attention block and then the multi-head attention. And now let's assemble the rest of the transformer. So let's now talk about these things called as the positional encodings. Okay, so what happens is, if there is a serious flaw with the current way of doing attention, and what is that flaw? We have kind of not respected the order. Currently it is just a set of words, it's not a sequence of words, it's permutational invariant, right? It treats it as a set of words and not a sequence. Order doesn't matter. And like dog bites man is news, but man bites dog is a headline. But we currently do not kind of differentiate between that, and we need to inject this positional information somehow. And there are two approaches: the original sinusoidal encoding and the more modern rope, and we'll briefly discuss both of them. So currently it's everything to everything, and the attention heat maps, whether it's man to dog or dog to man, it's exactly the same. Now in the original paper they had these so-called sinusoidal encodings, and for so you have, let's say, your token, and let's say token is this big, right? And token is a row vector. And now this position is the position of the token itself, right? So this is like the first token, this is the second token, and so on. And so this is the position. So this is, let's say, position 1, the second token is position 2, and so on. And this I that you see in the denominator, this I is the index in the vector itself. So here the I is equal to 0, 1, 2, and then all the way to whatever is the size of this encoding, let's say 512, okay, or 64, depends. So now we have this thing called as the, so what we do is we now have this additive. So what we have, let's say, let me draw it elsewhere. So let me draw it here. So we have our original, let's say, encoding. So this is our original encoding, right? So this is our original token, and this token is, let's say, at position 1. And then we have, this is 0, 1, 2, and so on, right? Let's say 64. And what we do is we add to the even positions this 2i upon d model. Let's say the d model, the dimensionality of this is, let's say, 64, right? So what we do is we do sine of position. Position is 1, so position for now is 1. And then we do, let's say, the I is 0, so we do 2 into 0 upon 64. So it becomes 10,000 to the power 0, which is 1. So we do a sine of 1. And then what we do is we, let's say, go to the value 32, right? So at 32, let's see what happens. So it's still 1, the pose is equal to 1 because this is still the first token. So what will happen is at 32, because it's still even, we will have 2 into 32 upon 64, right? So it becomes 1 upon 10,000. Right? So, and then let's go further away, right? Let's go to, let's say, 64. So then it becomes 1 upon 10,000 square. Let's say we go to 16. So it becomes 2 into 16 upon 64, right? So 2 into 16 upon 64. So 2 into 16 is 32 upon 64, which is 1 by 2. And 10,000 to the power 1 by 2 is 1 by 100. So we rotate it with 1 by 100. So the first one, we rotated it by 1. The 16th one, we rotated it by 1 by 100, right? So the sine of it. And then the last one, we only add the sine component of, let's say, 1 upon 10,000, right? So what we are doing here is we are essentially causing these ripples. We're adding these ripples. And what do those ripples look like? It looks like this. So initially, those initial elements of the vector, the initial elements of the encoding are fast moving, right? Because of that I. And the later elements are slow moving, right? So these initial elements, so this is, let's say, the dimension. So I'll just rub this. So this is the dimension of the vector, right? So this is the dimension of the vector. So this is, 1 to whatever 64, let's say. So here it's 64. And this is the position of the token, the first token, the second token, and so on. And we see that the first token, there's like a lot of change, right? And also in the first token, we see that, the initially, let's say the, 1 to 20, it's fast moving, right? The first to 20 elements of the vector is fast moving because the angle is big, and then the later part, the angle is small. And this is this addition. So we just calculate the sine and cos based on two things, based on the position of the token itself and the position of the element of the of that number in the vector. And based on that, we calculate this positional encoding, and then we do an addition of this positional encoding with the original token, with the original embedding. And with this, now these different tokens will have different encodings, right? Because the first one has position equal to 1. In the second one, we have position equal to 2. In the 20th one, we have a position equal to 20. So it becomes like double, 3 times, 20 times, right? Because the numerator changes based on the position of the token. And we then also do it for the vector itself. There were problems with this. The problem was that this is in some sense, addition. So the MLP stages later on, which we will talk about, and the other parts of the transformer later have to figure out how to remove this, right? Because you change the vector itself. So it has to kind of know how to remove that. But then these people, these rotary positional encoding people came up with something like better and simpler. And what they do is they say, okay, you kind of have this word sat, you multiply the x with the wq, you get your q, and the q has 62 dimensions, and then we divide these dimensions into pairs of size 2. Right, so 0 and 1 become 1, 2 and 3 become 1, 62 and 63 become the last one. And then we can have this Q0 and Q1 here, right? So whatever are those two numbers, we can plot it in 2D. Let's say this is Q0 comma Q1. And then what we do is we rotate it, right? And how much, I'll talk about it. And we rotate it, and think of this as kind of twisting, right? And again, it's the same equation, and we'll talk about this equation, but it's basically the initial, right? It's like a rope, and this is why the name rope, rotary positional encoding. The initial part has a lot of twisting, and the later part has less twisting, because the later part is slower, the initial part is fast. So initial part, the vectors are rotated higher, and the later part less. And why is this better? So here what we're doing is the vector is split into pairs of dimensions. Each pair rotates at a different speed, like a clock with different second, minute and hour hands. And this lets the model encode relative position at multiple scales. Almost all modern LLMs, including your Qwens and everything, use rope and the DeepSeeks of the world, right? So now the interesting thing here, what is happening is you don't have to do this addition. So the network later doesn't need to learn how to undo this addition. You're just rotating it. So the size of the vector is not really changing. It's just a rotation, right? And this is why it's elegant, because it's not encoding this absolute position like in our previous case. It's encoding this relative position. Right, so if you think about it, it gets clearer. But the point here is to just give you intuition, and then for more details, we will point you to the right resources in the rabbit hole and other description sections of this video. So we have now converted our sequence, from this set to a sequence, because now it's an order, because each token, each word, each token in the sequence now has a notion of position, right? So this was another building block. So we are done with this bit just now. So we are done with the positional encoding bit. We've already spoken about this. So let's talk about the feed-forward network. Feed-forward network is nothing but a fully connected network. It's really simple. So the way to think about this is, attention is like this communication, right? It's about calculating the scores by multiplying the keys and the queries, and then doing, the addition of the weighted sum of the values, and that is the communication part. But then we use this FFN, the feed forward network, to actually do the computation. And what we do is we do this at, we do this at the token level. So for every token, we now want to see how these different elements of the vector interact. And for that, we just put, let's say our token, the output is of size 512. And the way it usually works and worked in the original paper is you actually go up from here. For 512, you go to 2048. And then from 2048, you come back to your 512. Also, you use an activation in the middle, you use a ReLU, you use a GELU, you use a, some other nicer activations which we will talk about. But essentially, this is the FFN. It's essentially an MLP. It's a feed forward network. And again, there is no mixing across tokens, right? It is just at the single token level. And what is this channel mixer? This channel mixer, so the attention mixes information across time. So attention is basically the one which looks across tokens, but the FFN mixes information across channels, right? Across one token. So internal processing within that one token. And the architecture is just a simple MLP. And this MLP is applied to each of those tokens individually. And your embedding dimension, so 512, projects it to 2048, and then it projects it back down to 512. And if you wanted to write it down, suppose we were starting from here, you put a fully connected, you put an activation on top, and then you put a fully connected on top of it again. And that's it. And so attention is essentially looking around the room to gather cues, and FFN is processing those cues in your brain to reach a conclusion. And this is what the FFN does. And then there are two other tricks that we use, which is the residual connection. Residual connection helps with training these deep networks, right? Because you have so many layers in your transformer block, basically because of the flow of gradient, and learning, that it makes that identity learning easy. Because we say that if you wanted to learn identity, you can learn weights 0, it will still output identity. Another way of thinking these residual connection is to think that we are basically learning deltas on top of your input and not the complete output itself. So we use these residual connections within the transformer, and then we also do this layer norm. This layer norm was later replaced by RMS norm. We'll talk about it, but layer norm is again simple. What you do is you subtract by the mean, so of the token itself. So let's say you have a token, right? So this is per token. What you do is you compute the mean and the standard deviation of that token. Let's say the mean of the token is this and the standard deviation is this. You subtract the mean and divide by the standard deviation. You get this, right? So this is what we are doing here. We call it the normalized vector. And then we have these learnable parameters, the affine shift, the shift and the shift and the scale. So this is doing the scale, beta is doing the shift. And then the final output essentially, and this is a very simple differentiable function. During backprop, you can backprop into your gamma and beta, and you can learn the values for that, right? And then you can apply this learnable scaling and shifting. So these parameters that we have here, the gamma and beta, are then applied in a similar way. The gamma and beta are applied to the z, and the z is something that we calculated using the values of the token itself. And this is layer norm, really simple. One slight segue is this batch norm, which we did not talk about, and this takes us back to the weight initialization lecture. And in weight initialization, we really wanted our activations, the distribution of the activations, to look like a Gaussian. And back in 2015, people from Google, this Eoff and Zizagi, what they said was, okay, you want Gaussian, make them so. How? You just subtract the mean and divide by the standard deviation of the batch. So you take things across the batch and then you can also add these. So this is your x hat k, and then you can have again these learnable gammas and betas, right? And this can recover the identity. If you didn't want to change the activation at all, you can learn this using, alpha and the gamma and beta. Because if you didn't want to subtract the mean and standard deviation, you can learn gamma and beta such that it can undo that, right? And then the only difference between this and layer norm is that batch norm is happening over the batch, and in sequences we don't have this luxury because sequences can be of different length. So there are problems. You do padding and all, but then your statistics of the batch may not be as well behaved as in the case of these dense batches that we have for, let's say, CNNs. So in the case of sequences, we do it at the token level, and we do this thing called as layer norm. Really simple. And finally, this is new RMS norm. They're saying, okay, calculating the mean is additional work. This is 40% simpler, faster and simpler. All we want to do is, we don't want to do this. Instead, we simply want to, divide by the root mean square. So you do, your L2 norm, and you simply divide by that. And you also just learn this one learnable parameter for the scaling part, because now what you're doing is you're dividing, so you're squishing it, but then you can learn how much to stretch it by learning this parameter gamma, right? So it is even simpler than layer norm, and this is what we use in most modern models. So now we can talk about the full picture, and this is what the transformer is, right? So there is the training time and the test time. There is the encoder and the decoder. Let's talk about the encoder, right? So what is the encoder doing? The encoder is, let's say, encoding a sentence in French, je m'appelle, into some encoding, right? And what it is doing, it is taking our inputs. We have our input embedding, the tokens. To the token, it's applying the positional encoding. It is putting it into these multiple heads. Those multiple heads, then you concatenate the output. You have a fully connected with the WO. The output, you then do this residual, right? After applying that WO, you do the add, and then you do the layer norm. And then after the layer norm, you do the FFN, right? And after the FFN, you again do a residual and a norm. And here we have our KQVs. What we do is we give, the KVs. So the KVs from here can go into here. And when we do that, so then, we don't use the KV from the previous one. And when you do when you do this, it's called cross attention. And this sometimes, this bit you may not have all the time. So when you have an encoder decoder, you do this cross attention, and you get the KVs from here and the Qs from here. Now, let's forget about this for a second. So let's say that is what the encoder is, and a model which just does encoding is, something that we talk about next, which is, let's say, the BERT. So BERT is an encoder-only model. Okay, and what you want to do on BERT is, let's say, sentence classification. So you have your encoding, and then you can maybe do a classification on top of that. So it basically encodes your sequence of inputs. Now, what is your, let's say, decoder? So the decoder usually during training, it's shifted right? Because what you want to learn from the decoder is how to kind of predict the next word, right? So you want to have like a shifted output. And when you have a encoder decoder, your output is shifted. But when you have just the decoder, you basically do this one word at a time. You have that masked attention because you don't want to look at the future, right? So you have your tokens again here as input. You do the positional encoding, and then you have your masked attention head, you have your add and norm because you have your residual, and then you can either do your cross attention if you have an encoder, but for example GPT is a decoder only, and in your GPT you will not have this, right? But suppose you have it, then you get the output. In that case, you just do self attention here, right? You just don't do this at all, right? You just do this, and then you directly put it into the feed forward. And then if you have your cross attention after the self attention, you put that into the cross attention, and then you again put it into your FFN, and you do, your add and norm because you have your residual. And now you then kind of, you have your, so what you do is you take the last word in your context, and that kind of gives you the next word, right? And how do you do that? You take that and you project, you have this linear layer which is outside your transformer block, because these transformer blocks can be stacked one top of each other, right? Many of them. And what you do is you have your linear layer, and here it projects it into the entire vocabulary. Vocabulary is usually like 65,000 words. So now you have your 65,000 words, and now so this is a huge layer, right? Because if your embedding is, let's say, of size 1024, this is 1024 cross 65,000, and this is where you finally get the word, right? Suppose you were doing decoder only. So decoder only, you start with, let's say, just the first word, which is BOS, right? So you have, when you're doing decoder only, you have things like BOS and EOS. So what does BOS stand for? BOS stands for beginning of sequence. And then you have your POS, right? You can write it maybe like this, because these are special tokens. And you start with this, and then you kind of want to predict the next token, but currently you only have this, right? And whatever is, so you get this, and then you feed it back in. And you keep doing that, and when you get the last in the context, when you fill the context size, that is what then kind of gives you the next word in this sequence. And that is how decoder only architectures work. So encoder only is BERT, decoder only is GPT, and encoder decoder is your T5, right? Where you encode and then you also decode. And in the next video, we will talk about how this transformer architecture has changed over time. Actually, these people found a pretty good local minima in the architecture space. It hasn't changed too much since then. It has only changed a little bit, and we'll talk about what all has changed. For example, we use RMS norm. We do the norm pre the layer, not the post layer, right? Here you see the norm happening later. Now we do the norm here and here, and a few other small things, but that's about it. And then as an assignment, we do something really interesting. We do what we did previous week. We take our sequences of human pose, and instead of the RNN, we now apply the transformer. How, and that is when our understanding gets concretized, how to apply, let's say, a transformer to sequence data. Right? And we will only do decoder only. We will do a GPT type decoder only transformer, where we just want to decode the next frame, the next human pose in the sequence of human poses. And that's all there is in a transformer. It's not that hard.